Lesson 6.4, representing functions. Our objective for this lesson is to be able to represent a function in 3 different ways and to be able to describe the domain and range of a function. So let's define domain and range. The domain of a function is the set of values of the independent variable that both make sense and are of interest for the function. Now, in algebra class, you might have talked about the domain as all possible inputs for a function. And often the domain was something like from negative infinity to positive infinity, or all real numbers, or all positive numbers from 0 to positive infinity. Well, if you have a context for a problem, if this is a word problem, if there's some real world application for this, then it's not going to make sense to say the domain of this is from negative infinity to positive infinity. You only want the values that both make sense and are of interest for the function. So the domain is the set of values of the independent variable that make sense and are of interest for the function. The range, then, the range of a function consists of the values of the dependent variable that correspond to the values in the domain. So we first are going to look at what values of the independent variable make sense. And once we have that domain, then the range is going to be the set of all values that correspond to those values in our domain. Because remember, the dependent variable depends on the independent variable. And so once we have that domain, that's going to determine our range. We're going to talk about 3 basic ways to represent a function. The first is a data table. And usually when we represent a function on a data table, we have the independent variable on the left and the dependent variable on the right. So that when you read this table from left to right, you have the input and then its corresponding output. The second way that we're going to represent a function is with a graph. And on the graph, we're going to have the independent variable on the horizontal axis and the dependent variable on the vertical axis. And then finally, we can represent a function with an equation. And we're going to put these equations in function notation with the dependent variable represented by this function notation, f of x, and the independent variable is going to be what's inside this these parentheses, and it's also going to be the variable that is on the right side of the equation. Our example tells us that this table shows typical values you might find for atmospheric pressure at different altitudes, with the pressure given in units of inches of mercury. And we're asked to graph the function represented in the table, describe its domain and range, and use the function to predict the atmospheric pressure at an altitude of 15,000 feet. All right, so we can see here that when our altitude is 0, so when we're at sea level, the pressure is 30 inches of mercury. When the altitude is 5,000, the atmospheric pressure is 25 inches. At 10,000, it's 21 inches. At 20,000, it's 14 inches. And at 30,000, it's 9 inches. All right, so let's first start off by graphing these. And we can see down here on this graph, on the horizontal axis, we've put the altitude, which is the independent variable. And on the vertical axis, we've put the atmospheric pressure, which is the dependent variable. All right, and so we know that at an altitude of 0, our air pressure was at 30 inches of mercury. So we'll put our first point there. And then when the altitude is 5,000, we had a pressure of 25. So we'll plot our second point right there. At an altitude of 10,000, the atmospheric pressure was 21 inches. So we'll plot a point there. At 20,000, the atmospheric pressure was at 14 inches. So that's right there. And at 30,000, the atmospheric pressure was 9 inches. So that's going to be right about there. And now we can see what's happening with these dots. It's coming down, and it's an almost straight line, but not quite. It's kind of dropping a little steeper here and flattening out a little bit as you go this way. So we're going to draw this with that slight curve there. So we're going to kind of connect these dots so that it goes like that. All right, so now let's use this function to predict the atmospheric pressure at an altitude of 15,000 feet above sea level. So if we go to 15,000 here and we come up to where that point would be on that line, we can see that that's going to correspond to an atmospheric pressure of about 17 inches of mercury. So that's one way that we can use a graph to predict values that aren't included in our given values. All right, the last thing we're asked to do in this example is to describe the domain and range of this function. So remember, with the domain and range, we're looking for values that make sense and are of interest to us. So as far as the altitude, so that's our independent variable. So the domain is going to be the set of altitudes that make sense and are of interest to us. So the lowest altitude that would make sense would be Death Valley. No, sorry, the Dead Sea has the lowest elevation on Earth of about 1,500 feet below sea level. So negative 1,500 might be the low end of our altitude in terms of what makes sense. And then the high end, our atmosphere extends about 300 miles above the Earth. That's about 1.5 million feet above the Earth. So we could extend our domain all the way out to 1.5 million. But as far as what is of interest to us, well, that's going to depend on why we want this information. If we're a pilot, then we might have a domain here of, say, 0 if we're never planning on landing in an airport that's below sea level. 0 might be our low point, and we might want to go up to 30,000 or 40,000 because we're not going to be flying higher than that. And so any atmospheric pressures above that are not going to be of interest to us. As far as the range, well, the range would be whatever corresponds to our domain. So here, if we're going from 0 to 30,000, then our range is going to go from a low of 9 inches of mercury at 30,000 up to a high of 30 inches of mercury.